Participants already, welcome to tonight's webinar, mathematics webinar. We're really excited to have Dr. Zoe Wyatt with us today delivering this webinar, and I think it's going to be by the title, I think it's going to be a really fantastic hour. Fantastic. The last thing to say before we get started is that I'm going to be moderating the Q&A. There's a Q&A down the bottom there, or it's on the bottom of my screen at least. If you have any questions throughout the webinar, please do pop them in there, and I'm going to have a look. And I imagine there might be quite a lot of questions, so we might not have time for all of them, but I'll choose some that I think look really great, and hopefully at the end I can ask Zoe those questions and we can get them answered. Fantastic. So aside from that, I'm going to stop waffling on and I'm going to pass over to Dr. Zoe Wyatt, who is delivering her webinar. Zoe, thank you so much, and over to you.
Hi, thank you. Sorry, just some IT things. Okay. Hi, everyone. Thank you all for coming. It's very exciting to do this webinar, and I hope we're going to have some fun talking about some maths. So my name is Zoe, and I work in the Department of Pure Mathematics and Mathematical Statistics, which is one half of the maths department here in Cambridge. And I'm also a college lecturer at Murray Edwards College. So today I'm going to tell you a few things, and I thought I'd just start with a little slide here about the Cambridge Maths degree. Maybe just a couple of things about maths to get us going. So if you can maybe hear from my accent, I'm from Australia. So to me, the Cambridge system is very different to let's say what we have in Australia, and maybe also for you, it's something that you're not as familiar with. Okay, so we have 3 terms in Cambridge, which get these funky names: Michaelmas, Lent, and Easter. Okay, and we also give special names to your year level. Okay, so if you're a first year student, you're doing part 1A of the Cambridge Maths Tripos. If you're a second year student, it's called part 1B. If you're a third year student, it's called part 2. Now, if you're a mathematician, you might be thinking, well, Tripos has tri in it, so where's part 3? Okay, and that's what we call the master's year. Okay, part 3 in Cambridge is what the master's degree is referring to. Okay, so hence the tri there. Now, the mathematics department in Cambridge is split into 2 parts. Okay, and the first part is, or first kind of half of the department is called DIPMS. So the Department of Pure Maths and Mathematical Statistics, that's where I work. And there we, as the name says, we've got some pure maths, mathematical statistics, those kinds of topics. And then we also have the other half of the department, which is called DAMPT, okay, Department of Applied Math and Theoretical Physics. Okay, and so parts of mathematics that are more applied in nature, they sit in that department. But the great thing as an undergraduate, okay, is that you get to take courses across the pure and applied spectrum. Okay, and maybe you're like, already I know I want to do pure, but I can assure you that might change when you get to university, and that's a really great thing to study courses from both of these areas. So let me tell you a bit more about what you do in first year. Okay, so courses in 1A, that's the first year of the Tripos. Okay, so here I've actually just put the Michaelmas and the Lent terms. Okay, so just to make it a bit easier. So in term 1, for example, you would do a course in vectors and matrices, in differential equations, in groups, and in numbers and sets. Okay, this final course, mechanics, is something a bit different. And in the second term, you would do a course in analysis, in probability, in vector calculus, and in dynamics and relativity. Okay, so this is a really great mixture of courses that sets the foundation for a degree in mathematics. Okay, you've got some courses here that set foundations in pure maths and courses that set foundations in applied maths. So you get a fantastic spectrum here that kind of equips you with lots of tools and ideas and concepts that you can then use to go into more specialized courses in your second and your third year and possibly your fourth year. So this is a list of courses that we have. And I should just say in your first year, these are all compulsory. Okay, and maybe I just, with my pen, highlight the mechanics course is not compulsory. That's a bridging course for students that haven't done as much mechanics at school. But all these other courses here in your first year are compulsory. And that's a good thing. Okay, that's actually a really good thing because you get to learn a lot of different ideas that you don't quite know where you will need, but you will need later on in your degree. You will need in your second and your third year. Okay, so it's some kind of big mixture that you get to study in the first year that is very fun. So I thought today in this webinar, I would tell you a little bit about some of the maths that you get to learn in some of these courses. Okay, in particular, I wanted to talk about an idea that you meet in numbers and sets. Okay, and this idea, which is going to be the notion of a limit, okay, then feeds into the course analysis 1 in the second term. Okay, and then I'm also going to talk a little bit about this idea in analysis 1 and how that feeds into a concept or something that you study in the course dynamics and relativity. And actually this then feeds into my own research, and that's what I'm going to tell you about at the end, which is how to bake a black hole. Okay, so this is one of the great things about maths. A very important thing to realize about maths is that it's very cumulative. You learn things in you're learning things in high school that you will use in the first year of your undergraduate. And then you will learn lots of different things in your first year of undergraduate that then get kind of combined together into different topics in later years. Okay, so maths is a very cumulative subject, and that's in some sense why the courses in first year are compulsory, okay, because we really need you to kind of tick off lots of things and learn lots of ideas so that we can rely and build upon them in later years of the course. Okay, so let's talk about a little bit of maths. Now I just need to click that. There we go. Okay. So the big idea I wanted to tell you about today is something called continuity. Okay, so continuity, this word here, is a concept that you will meet in analysis 1. And it's, at its essence, let's say, it's a way for us to distinguish between the two functions that I've drawn on this slide. Okay, so we look at this function, this one on the left, it's this nice parabola type shape. Everything looks very pretty, okay, but we can tell that it's a very different kind of function to the one on the right. Whereas the one on the right, I kind of come down and then, oops, I jump and I come up like this. Okay, so these two functions are, just from looking at them, they're quite different, but they also have lots of different properties. And we'd like to, let's say, have a mathematical way to distinguish these two functions, to understand, classes of functions that look a bit more like the one on the left versus ones on the right where we have this jump, okay, where something is clearly quite different on that side. Okay, so to make this precise, we're going to need an idea from the numbers and sets course. So this is the one of the courses in the pure side that you will do in the first year here in Cambridge. Okay, so the first thing I want to do is I want to talk about the limits of sequences of real numbers. Okay, now you might have already met this in school, but you also might not have. So let's talk through this. Okay, so I'd like to take a sequence of real numbers, x1, x2, x3, all those kinds of things. Okay, so as an example here, I've got the sequence xn is equal to 1 over n. Okay, so the first element of the sequence is just 1, and then I've got 1 over 2, and I got 1 over 3, and I got 1 over 4. Okay. So I'm going to actually plot this sequence like this. So on the x-axis here, I've got n, the integer n. Okay, and the red dot shows the value of the sequence at that point. Okay, so x1 is equal to 1 over 1, that's the number 1. And then I've got the number a half, and then I've got a third, and then I've got a quarter. You get in the picture. Okay, so what do we notice about this sequence? Okay, it's a very nice one. It's just 1 over n. That's pretty nice. We notice that it gets smaller and smaller. Okay, and the numbers get teeny tiny as n gets very big. Okay, and we could kind of draw a picture like this. We could draw a line if we wanted, and we would see that the value of the sequence, as it's getting smaller and smaller, it's tending, looks like it's limiting to a number, which we call the limit of the sequence. Okay, and that limit in this case, just by looking at it, has got to be 0. Okay. So this is the idea of a limit. You think in English, you kind of push yourself to your limit. You go as far as you can. We have the same idea here in maths. I want to see that as I let this integer n get very, very large, sending it off to infinity, I want to ask myself, what does this sequence limit towards? Okay, so I should just say that all these pictures I'm going to use today, you can find on GeoGebra, an applet made by someone called David Richardson, and they're truly fantastic applets. Okay. So let me give you another sequence. Okay, this one is a little bit more complicated. Here my sequence xn is equal to 5 times sine n over 3 times 1 over the square root of n. Okay, a lot of things going on there, plus 1. Okay, so this is a different kind of sequence, but again, we could put in values of n. Okay, so I guess x1 will be 5 sine 1 over 3. I can't write fast enough, can I? Over the 1 over the square root of 1 plus 1. Okay. But now I want to think, okay, well, this is a different kind of sequence. Does it also have a limit? Okay, so now I'm going to show you a graph of this sequence. So again, on the x-axis here, I've got the integer n, right? And then on the y-axis, I'm plotting xn as a function of this integer n, okay, as a function of n. So what do we see in this graph? We see lots of red dots, okay? And we also notice that the dots, they have this actually very quite pretty, isn't it? This oscillatory behavior. Okay, so that oscillatory behavior is coming from the sine factor. Okay, we know that sine oscillates, the sine function is oscillatory. But what else do we notice? We see that the amplitude of this oscillatory factor is decreasing in size. You know, the amplitude, the height of these oscillations is decreasing in size. And that's actually coming from this factor here, 1 over the square root of n. Okay, as n gets large, as n gets really, really big, okay, this would be 1 over the square root of a really, really big number, which is really small. Okay, so this factor here, this 1 over the square root of n, is becoming very small. Okay, so this is why the amplitude is decreasing in size. So that's good to see. And what else do we have? Well, we've just got this 1. Okay, and this 1 is just sitting there. Okay, and actually that's why I've drawn this yellow line here for 1. Right, and that just sits there. That doesn't do anything. Okay, so in particular, it turns out, and we're going to talk about why this is the case, but it turns out that this sequence tends to the limit a is equal to 1. Okay, and that's because this sine factor here oscillates, the amplitude is getting smaller and smaller, and so this first term here involving sine and the square root of n, this is tending to 0. Okay, just like 1 over n was tending to 0, this term is also tending to 0, and what are we left with? We're left with the number 1. Okay, so this is great. I can look at this picture and, you know, I can see what's going on, but we're mathematicians, right? We don't want to just be drawing pictures, even though it's very good to always draw graphs and pictures. We want to do something kind of mathematical and quantitative. Okay, so what do we want to do? We would like to measure the difference, okay, between our sequence xn, the sequence values, and the limiting value 1. Okay, I'd like to measure the difference between these red points here and the limit, which is 1. So we see at the start, this difference is quite large. Okay, that difference there is pretty big. But then if I take later points in my sequence, if I come down here, let's say where n is equal to about 42, okay, this distance here, this distance is a lot smaller. Okay, and the modulus is measuring that distance. Okay, it's measuring the difference between the red point, okay, the sequence value, and 1. All right. So what I do on this picture now is actually I'm going to draw some shaded regions. Okay, and in particular, this shaded region, this yellow region here, shows the sequence values where xn differs from the limit 1 by at most, let's say, 1 unit. Okay, so these yellow bands here have got each side is of length 1. Okay, I've got my limit in the middle. Okay, and so I'm now looking at sequence values where I'm within this yellow band. Okay, so we see at the start here, I've got these red points. They don't fall inside this band. Okay, but I've also got a lot of green points, and they do fall within this band. Okay, which means that for these sequence values, okay, xn minus 1 is indeed strictly less than 1. Okay, nice. And that's good, right? Because if we were expecting this sequence to be tending to 1, well, we'd really expect that lots of points would be getting closer and closer to 1. So let me show the next picture. So in this picture now, it's the same one as before, but now I've zoomed out. Okay, so now we can see a lot more sequence values. So this is n going off to 100, and n is getting very large here. Okay, so what happens here, we've zoomed out, and we see that at the start, for small values of n, okay, here n is about 10, here n is about 25. Okay, we get these red points. And so that means those sequence values are more than 1 unit away from the limit 1. But then we see from this point onwards, we're just getting green sequence points, green points here. And so that tells us that all these sequence values do indeed satisfy this inequality. So in fact, you can show, right, which I'm not doing here, but you can show, for example, that for any n bigger than about 24, okay, so 24 actually might be about 26. I might have not entirely drawn it right. So let's say we need to draw a line here. From this point onwards, for any little n going this way, remember that the x-axis is going this way, we have, in fact, that xn minus 1 is strictly less than 1. Okay, so we've controlled the sequence, and we say, look, it's not yet equal to the limit, let's say, but it is at least within 1 unit away from it. So that's pretty good. Okay. So this was all for the threshold here, the width of my band. This yellow band here had, well, it has width 2, okay, and on either side of the limit, I've got a size 1. But we could do the same thing, but with a smaller threshold. Okay, so what I've done now on this graph is I've done something very similar, okay, the same thing. All right, but what I've done now is I've chosen a smaller threshold. Okay, so before I was looking at sequences that were within 1 of the limit. And now I'm looking at sequence values, sorry, where I am within 1/2 of the limit 1. Okay, so that's why here I've got my limit, which is 1, and then I go above it to 1.5, and I go below it to 0.5. Okay, so now we actually see we don't have as many green points, do we? We have a lot more red points. Okay, we still have red points at the start. That hasn't changed. We've still got red points there. That hasn't changed. Ooh, got a lot more red points there. Ooh. Doesn't look as good, does it? Yeah, not as many sequence values. Not as many sequence values lie within this smaller threshold, this smaller band. Okay, but all hope isn't lost. Okay, because if I zoom out some more, actually things look better. Okay, so now again, I am showing the x-axis going this way is the parameter n. Okay, and for each integer n, I am plotting this sequence. So actually on this plot, we really get this nice picture of this sequence. Okay, we see this oscillatory factor sine. These oscillatory factors coming down here. That's very good. we see the effect of 1 over the square root of n, okay, which is making the amplitude here smaller. Hence why these amplitudes are coming down and decreasing and decreasing. And then we also see the fact that the whole sequence is kind of shifted up by 1. Okay, so sine, if we were to draw sine, it would be centered around this x-axis. Okay, but because we've now got this extra factor of 1, everything's been pushed up by 1. Okay, so we get a very nice picture here of the function, of the sequence, sorry. Okay, so what do we see here? What were we doing? We see here the yellow region shows sequence values where xn minus 1 is less than a half. Okay, so that's a more refined threshold. Okay, that's kind of, we want to know sequence points, which are sequence values, which are even closer to the limit. They're within half a unit of the limit. So now I can actually do something very similar to what I had before. And I can introduce this new region in blue. Okay, and what does this region in blue show? The region here, this line here is coming in at about 62. Okay, and it says that for any n bigger than 62, all the sequence values from then onwards will be within 1/2 of the limiting value 1. Okay, so all the sequence values here henceforth will be within the value, be within 1/2 of the limiting value 1. Okay, so these pictures are all behind what you will meet in the first part of numbers and sets, of course, in 1A here in Cambridge, okay, which is what is called the definition of a limit, okay, or the concept of a limit. So here we write the limit xn tending to a, right, as this integer n goes off to infinity. And we say that xn tends to this limit, okay, if for every epsilon, okay, for every epsilon, as big as you want, as small as you want, okay, there exists a finite number, capital N, such that xn minus the limit is less than this threshold number epsilon for all points henceforth in the sequence. Okay, so what I've done is, this is a very kind of standard first kind of definition that you'll meet in a maths degree. Okay, but we see that here it looks very dry. Okay, lots of symbols and letters going on here, but actually it's visually, it's very clear what's happening. Okay, so we picked epsilon to be 1, and then we picked epsilon to be 1/2. Okay, and so in the case when epsilon was 1, we found a finite number capital N that was about 24, okay, such that xn minus the limit a was less than or equal to 1 for all subsequent points in the sequence. And we did the same thing for 1/2. Okay, we found a finite number capital N that was about 62, I think, such that for all the difference between xn and the limit 1 was less than 1/2 for all subsequent points, all those blue, the region marked in blue, and for all those subsequent points in the sequence. Okay, now obviously we don't want to be going and drawing plots for epsilon being 1, epsilon being 1/2, being 1/4. We don't want to, we're mathematicians, we like to conserve energy, let's say. So we need to prove that. Okay, now today I'm not going to go through how you would prove that properly. Okay, but that's what you get to do in numbers and sets. Okay, is to prove things like this, to prove that that sequence that I gave you actually does indeed tend to this limit A. All right, now you might say, look, Zoe, that's great, but it's a bit boring, right? I want to do cool maths. Okay, and that is true. All right, there's sometimes in maths we've got to teach you lots of basics before we can show you the really cool stuff. Okay, so what is one very cool idea in my mind, which is what we'll turn to next, is this idea of continuity. Okay, so remember, this is what I wanted to talk about, was this notion of continuity, something that differentiates this graph on the left with this hoppy graph. It's one that's got this jump on the right. Okay, now it turns out that the function on the left is going to be what's called continuous. Okay, and then the function on the right is going to fail to be continuous, and that means we call it discontinuous. Okay, so let me give you some intuition behind continuity. So our first intuition is that a continuous function, we should be able to draw a continuous function without taking our pen off the page. Okay, so when I draw just some nice function, something like this, I'm not taking my pen off the page. There's actually a lot of functions that will satisfy that. But there's also a lot of functions that don't. Okay, so here I've got the graph of 1 over x. All right, now 1 over x for positive x values comes along like this. But I probably should have done it the other way. Let's say I come from the right, I draw it here. This is my graph of 1 over x, goes off to infinity. Whoop, I have to take my pen off the page so I can come back down here and carry on the graph there. Okay, so this is not going to be a continuous function. This is going to be a discontinuous function. Another intuition, another idea behind continuity, okay, is that a small variation of the argument should cause a small variation of the value of the function. So probably easy here if I put up the picture. Okay. So this is saying that if I pick a point, let's pick the point 1. Okay, and I look up, I come and see what value of 1 I've got here. I've got this value here. Okay, 3/4, something like that. Now, if I take a nearby point just below 1 or just above 1, and I look at where these points get mapped to, well, they just get mapped to nearby points. Okay, so a small variation of the argument down here leads to a small variation of the function value up there. Okay, that's going to be an intuition, an idea of what we want a continuous function to satisfy. And we see here that something clearly is going to go wrong at 2. Okay, so at the value of 2, the function value, let's say it comes here. Okay, now if I take a small variation to the right, my function value just comes down slightly. Whereas if I were to take a small variation to the left, well, my function would actually jump up significantly higher. Yeah, it's not a small variation going from here up to there. Okay, so this function will also fail to be continuous. So let me give you the definition then, okay, of what a continuous function is. All right, and this definition is going to use that idea that we met of a limit. Okay, and again, I'm telling you this because this is kind of a simple example, but this happens so much in a maths degree. Okay, you will learn something 1 year in 1 semester, and then you'll use it 2 years later. Okay, and you'll learn it at the time and not realize why you were taught that. Okay, so we say that a function f of x is continuous at the point A, all right, when the following holds. Okay, the statement is that if I have a sequence xn that tends to A, as n tends to infinity, okay, then the function values f of xn, which is also a sequence indexed by this integer n, this should also tend to f of A. All right, so this is telling us a few things. It's telling us that f of A should be a finite number. It should be well defined. It's telling us that this limit, this sequence here has a limit. And then it's also saying that the limit of this sequence, f of xn, is equal to f of A. So this very simple definition has hidden within it three things, right? And this is actually what happens when you go to university maths. A lot of things are like this. There'll be a lot of hidden meaning in certain definitions and statements. And that's part of the joy of maths, is uncovering these and understanding them. Okay, so a definition. So here we have this definition. F is continuous at a point A when the following holds. So here I've given us the graph of cos of x. Okay, and indeed, cos x is continuous at every point. Okay, let's say in my first intuition, I've just drawn it without my pen lifting from the page. That's very good. We can see here small variations in the X value leads to small variations in the Y value. Okay, and in this course in numbers and sets, you will also prove it using this, let's say this proper definition that I put here. Okay, you can show that if ever you have a sequence xn that's tending to a point, maybe it's tending to the point 0, then you can show that the function values will also be tending to the function value at 0. Okay, so f of x is continuous. Sorry, f of x is equal to cos x is continuous. But as we've seen, it's quite easy to have function values or functions that are not continuous. So here again, we had the function 1 over x, and this fails to be continuous at x is equal to 0. So for example, because f of 0, okay, here is, let's say, not defined, right? So it's infinity, all right? And here we're talking about real valued functions which don't take on the value of infinity. Okay, so this is an example of a discontinuous function. And we've also got the other example that we talked about, this one with the jump. Okay, so here we've got this jump function. We come up and then we jump down. I took my hand off the page to do that. Okay, I didn't keep my hand on the page. And this indeed is a function that is discontinuous. So to prove that, actually, we could take a sequence of points that tend to the number 2. Okay, so for example, our sequence could be 2 minus 1 over n. Okay, so that means I would have points here that are tending, getting really, really close to 2. And what do their function values tend to? Well, their function values would be coming up here, and they would be tending really, really close to that number there, whatever that is, 0.9. But this statement says that f of x is continuous if for all sequences that tend to this number a, then f of xn tends to f of a. So now I can have a sequence that approaches the number 2 from the left, but I could also have a sequence that approaches the number 2 from the right. What would that sequence look like? It would be 2, let's say, plus 1 over n. Okay, 1 over n is tending to 0, so 2 plus 1 over n is tending to 2. So I could have my sequence here. It's got different points coming in, getting closer and closer, coming towards 2 from above. Okay, and what do I see here? I see that the function values are coming up, but they are tending towards this number, which might be about 0.6. Okay, which is not the same as this number up here, which is about 0.9. Okay, so that shows that this function here is discontinuous. All right, so this is our notion of continuity. And now what I want to do is turn to an applied course and tell you where that comes in, okay, where we use this notion of continuity. So the course I want to focus on is this one in term 2 called Dynamics and Relativity. All right, so let's have a little change of scene. Now I'm going to talk a bit more about an applied course. So in this applied course, Dynamics and Relativity, one of the topics that you will learn about are Newton's laws. Okay, so Newton's second law here tells us that the force, okay, is equal to mass times the acceleration. Okay, now you can apply this to lots of scenarios, lots of physical systems out there. But today I want to think about the dynamics of a mass on a pendulum. Okay, so here I've got a pendulum with a little weight on the bottom. And I want to think what happens if I start my pendulum at some slight angle and then I kind of let it go, and then it will just kind of oscillate back and forth. Okay, so we can use Newton's second law to determine the dynamics. Okay, what do I mean by dynamics? I mean that I would like an equation, because I'm a mathematician, I would like an equation that tells me where does this little mass go? You know, kind of does it go there, does it go there, kind of how does it move, right? I would like an equation that can model such dynamics. So you do what we call a force resolution. Okay, maybe that's not the best way to call it, but we take here Newton's law. All right, now here we have a vector quantity and here we have a vector quantity x. Okay, and we're going to apply this law in one particular vectorial direction. Okay, and in particular, we're going to apply it in this horizontal type direction. Okay, so actually, if I look here at this point, rather, it's going to be this direction here. Okay, so what are the forces acting on my little mass here? I've only got the force of gravity. Okay, in this scenario, I've not put in any friction or anything else, so I've only got the force of gravity. Gravity always acts downwards, like this arrow points here, mg. Okay, and so I can decompose this vector into a piece which lies in line with the pendulum itself. Okay, in line with the rod, let's say. And I can also decompose it into the little blue arrow here, which is perpendicular to that line. Okay, so this force is acting downwards, okay, which is why I have a minus here, right? And the force, the magnitude of this little blue vector is going to be mg sine theta. Now, I haven't actually told you what theta is, but hopefully you can work it out from the picture here. Okay, theta here is going to be the unknown that I really want to study. Theta is the angle that describes where this pendulum is situated. Okay, if theta is very large, it comes out here. If theta is 0, it's lying flat down there. Okay, so we end up with this force that is acting perpendicular to the rod. Okay, and that force is given by mg sine theta. All right, that's all very good. What do we do on the right-hand side of Newton's laws? Well, we need to look at the position, okay, and the position, and we've got some mass, okay, as well. All right, and the position here is going to be measuring this arc length. Okay, how large is this length? All right, so the arc length here is given by L times theta. All right, so that's why in this term here I've got L times theta. All right, so from Newton's law applied to this model, right, we get this system, this differential equation that I'm just circling right now. Now, the unknown in this equation is theta. Okay, L is a constant, M is a constant, G is a constant. So the only unknown in this equation is theta, which depends on time. And now we do something which you do a lot of in applied courses. Okay, when we want to model the world around us, we can't be as exact as we'd like to be. We often have to make approximations. So the approximation I'm going to use is using the fact that theta in this scenario is going to be a small number. Okay, so this is going to be theta is going to be a small number, and I'm going to approximate sine theta by theta. Okay, and this is an approximation that's valid for small theta, and you can prove this using something called the Maclaurin series. So if I substitute in sine theta is approximately equal to theta, then Newton's law gives me the following differential equation. Okay, so this is a differential equation, d theta dt squared is equal to minus g over L theta. Okay, so you'll notice that I had an L here and a G here. Okay, and I've put them onto one side of the equation. That's why now I get minus G over L. Okay. So now differential equations in such a setting, we can actually solve explicitly. Okay, that's why we made this approximation on sine theta, was again, we could get to this differential equation, which we can solve. Okay, and this differential equation says I take the second time derivative of a function, and I should get minus some number times that function. Okay, so when we differentiate, for example, cos, I get minus sine, and when I differentiate minus sine, I get minus cos. Okay, and I could also do the same thing with sine. So in fact, the general solution to this equation is given by this expression here. Theta of t is equal to some arbitrary constant C1 times cos of something plus C2, some arbitrary constant C2 times sine of something. Okay, now let's think. Here we've got this square root. Where's that coming from? Well, when I differentiate cos, I need to bring out this factor. And when I differentiate it again, I have to bring out that factor again. So I've got two copies of the same thing with a square root. And so that's what gives me this overall factor here of G over L. Okay, now we've got the general solution now to this differential equation, which gives us the general solution to which describes the pendulum motion. Okay, so now these constants C1 and C2, as you've probably met before when you've, let's say, done integration and things like this, we can fix these using boundary conditions, using initial conditions in this case. All right, so let us just suppose for this example that our initial conditions have 0 initial angular velocity, okay, which mathematically means that at time is equal to 0, my starting angle is going to be alpha. Okay, so my starting angle is going to be alpha, and then I'm just going to drop the pendulum. I'm not going to give it any velocity. Okay, so theta dot at t is equal to 0 is equal to 0. Okay, so these are initial conditions. These are, things that let's say the physics of the problem would tell you what to pick. And in this case, if I take these initial conditions, then it turns out that C1 needs to be equal to alpha, okay, and C2 needs to be equal to 0. Okay, so I have solved then the motion of my pendulum. Okay, in this scenario with these initial conditions, all right, the motion is described by this function here, where now I've put C1 is equal to alpha, and I've lost the sign term because I've set C2 to be equal to 0. Okay, so the motion of my pendulum, let's say it starts at this angle here, alpha, all right, is given by this function, and this angle theta oscillates back and forth. Yeah, cos gets bigger and smaller and bigger and smaller, and that's exactly what we see here. The angle gets bigger, and then it gets smaller, then it gets bigger, and then it's smaller. Okay, that's great. All right, maybe that's something you've met before in a course in physics. Let's say if you're doing physics at A level, maybe not. Okay, that's again one of the benefits of this first year in Cambridge is that you do lots of these topics that maybe you've met before, maybe you haven't, and it brings you all up to this same standard. Okay, gives you all that same knowledge. But now I want to tell you a bit about how we can put these two ideas together, this idea of continuity and this idea of a pendulum behavior. Okay, and the first thing to note is that this solution, theta of t, this function is a continuous function. Okay, cos is a continuous function, as I drew earlier in one of the slides. Now, in fact, we can also view this function theta not just as a function of t, but also as a function of the initial angle alpha. Okay, so the initial angle was alpha, that's my starting point. And I could view theta as a function of t and alpha, which is just the same function, but now I view it as a function of two variables. Okay, now in fact, this is continuous in both the parameters t and alpha. Okay, now this is a very important concept that we see a lot in physics. Okay, when we observe a lot of physical phenomena, we see a notion of continuity. Okay, if I do a small change in this initial angle alpha, okay, if I have my pendulum, it goes back and forth. And if I slightly change alpha, if I make that angle slightly bigger, well, my solution just goes slightly larger. Okay, I have some small variation in the solution given a small variation in the initial angle alpha. Okay, and you see this all the time. It's not like when you have a pendulum and you're swinging it around, it's not like all of a sudden you do some very small change here and your pendulum kind of goes upwards. Yeah, it doesn't do that. At least in this regime here of, let's say, of small theta. Okay, so this is a very important concept in physics, and in mathematical physics and maths in general, and physics and research and all these things, and it's the notion of stability. Okay, so stability means that the solution depends continuously on the initial condition. Okay, so for the pendulum, we had this initial angle alpha, all right, and then our solution, which was a function of alpha and t, depended continuously on that initial condition on that parameter alpha. Okay, and this notion of stability arises, as I've said, in lots of maths, physics, and research. And so now I'm going to tell you a little bit about some of my research, okay, which actually means that we have to jump ahead to a later part of the Tripos degree, okay, and into a course called General Relativity. Okay, so this is something that you could study in part 2 if you want. Okay, at that point, all the courses are optional, so you can pick and choose what you want. Okay, and general relativity describes or is Einstein's theory of the gravitational force. Okay, so earlier on we were talking about Newtonian gravity. That's Newton's theory of the gravitational force, right? And then Einstein's theory makes some slight modifications to Newtonian gravity, okay, which kind of is important in various scenarios. For example, to describe our universe, okay, and to describe very accurately how GPS satellites orbit planet Earth, and to describe very accurately how Mercury orbits the sun. Okay, so very, very accurate kind of precision type experiments. To make these accurate, we need a refined theory of the gravitational force, and that, to the best of our knowledge, is Einstein's theory of general relativity. Okay, so again, like we had before with the pendulum, we had some very important equations, right? We had d theta squared dt squared is equal to something. Okay, the main equations in general relativity are something called the Einstein equations. So I've written these equations here. Now it doesn't look it, but these are actually a system of differential equations, and they're quite a complicated system of differential equations. And when we make things complicated in maths, we typically add the word quasi or we add the word partial. Okay, so in this case, we've added the word partial. All right, so this is what's called a partial differential equation, right, which is a more complicated type of equation that you've probably not met yet in A levels, but you will in the first year in Cambridge. Okay, so this is a system of differential equations, and you might say, well, can we solve it? Just like before, I had the solution, which was cos of something. Well, we can solve it, right? We can solve these equations. And one of the solutions to these equations is called a black hole. All right, so you've probably heard of black holes, very popular topics out there. Okay, so one of the solutions to this system of partial differential equations is called a black hole. Okay, and we use it to describe what we believe are black holes out there in our universe. Okay, now a black hole, you can write down a very rigorous mathematical definition, but let's say intuitively, it's a region where the force of gravity is so strong that not even light can escape from it. Okay, so one of the big ideas in Einstein's gravity compared to Newtonian gravity is that the gravitational force can act on massless matter. In particular, it can act on light. So what I'm drawing here in these circles is supposed to be the sun. Okay, it's a very big, massive object. And it turns out that this mass of this sun, okay, produces a gravitational force which acts on light that passes nearby. Okay, so this is something called light bending, and was one of the first experimental verifications of general relativity. Okay, so I've got this very, very massive object, and light, let's say from a distant galaxy, has been emitted and it gets bent as it goes past our sun. Okay, now for a black hole, we have a region where the force of gravity is so great that even as the light tries to escape, it gets trapped. Okay, so the light is trying to escape, and somehow the force of gravity is so strong, it bends the light, instead of the light just going on a straight line like it would like to. Okay, it bends the light and it brings it back. So what this means is that a black hole does not emit light, right? Which means that it's very hard to draw a picture of these things. And so that's why you might have seen this picture in the news, right? It comes from an experiment called the Event Horizon Telescope. And it shows the region around a black hole, okay? But the black hole is the bit we can't see, okay? It's the thing in the inside, right? This is where the black hole should be. Okay, and the force of gravity in there is so strong that the light cannot escape from it. Okay, and so what we have outside of this is, you know, other types of matter that, let's say, is kind of dispersing away or might eventually be eaten up by this black hole. Okay, so this is a beautiful theory of black holes that you could study in the 3rd year and also the 4th year of the Cambridge degree. And there is a very important mathematical research question, which is to say, well, we have this black hole. It's a solution to a system of differential equations. Is it stable? Okay, is it a stable solution? So in particular, imagine I've got my black hole and I add to it a small kind of perturbation, a small wobble, a small piece of energy, something like this. Let's say it eats up a little planet or something like this. And that will cause the black hole to have some wobbles. Okay, but if this is a very small variation, then we would expect the solution to depend continuously on this small change in the initial condition, which means that the solution should maybe only slightly vary. And in fact, this question is even more subtle, let's say, is we then say, well, does this solution, this slightly perturbed solution, does it actually converge back to another black hole? Okay, it might be a slightly bigger black hole this time because it's eaten up this initial piece of matter. All right, but this is a very important open question in research, is saying, well, if we make a small change in the initial condition, does the solution only change by a small amount? Okay, so some small initial perturbation to this black hole. I wobble it slightly, I give it a bit of energy. How does the black hole change? Yeah, how does this solution change? And so this is a very active area of maths, particularly here in Cambridge. Okay, and I think I can almost end now by saying, how is this related to baking? Okay, I think it's a nice analogy to think of, all right, is the following. Okay, when you bake a cake, you have ingredients. Okay, you've got lots of ingredients, you've got your eggs, you've got your flour, things like this. And you know that when you put them together, you get a cake. But you also know that small variations in your ingredients typically don't lead to wild variations in the cake. Okay, and so typically baking, okay, is typically, not always, I know, a stable process. Okay, so we have this idea for maths, and we also see it in baking. It's this notion of stability. It's really in the world around us. Okay, so I'm almost done. And I guess just to summarize today, I've told you a few things from numbers and sets. Okay, we've met the notion of a limit. We use that notion of a limit to define continuity, okay, which is what you will meet in this course analysis 1. And then we've also talked about Newton's laws of motion coming from the course dynamics and relativity. Okay, and in that we get some solutions to describe the motion of a pendulum, and these are continuous functions. Okay, and this fact that they're continuous is very important for this idea of stability. Okay, so these are all kind of hopefully some interesting things there that you've learned about. And I guess before I end, I just wanted to give one teeny little word on the interview, okay, because we do try and interview as many candidates as possible who apply. Okay, so I do very much encourage you to apply for maths and very much hope that you'll be selected for an interview. But I just want to mention that some of the questions that we ask, they're going to be a bit of a step up from what you've met in A-levels. Okay, and I just did a very naive Google search, okay, and I found a lot of results. Now, I'm not saying all those things out there are the best things written, but I really do encourage you to do lots of practice questions online. Yeah, find questions. There's lots out there from Oxford and Cambridge, okay, and try and do as many of these as you can. All right, don't come in thinking that we're just going to ask you some standard A-level questions. We're really going to try and push you, and you could be great, but it's very important to prepare for that. All right, so with that, I will thank you very much for your attention, and if we've got any questions, I'll be happy to answer them.
Thanks so much, Zoe. That was fantastic. I've noted down a couple, Zoe. The first one was sort of actually around studying maths at Cambridge, and it is, do students at the Department of Applied Maths and Theoretical Physics still have access to labs and conduct their own experiments?
Right. So the short answer is no. Okay. If you, oh, actually, no, sorry, let me take that back. The short answer is it's a little bit complicated. In your first year, you can do an option called Maths with Physics. Okay. And you get to take, you don't take all the maths modules, you take out some of these and you do some physics modules. And in those physics modules, you will do experiments. But there is also a fluids laboratory in the Department of Applied Maths and Theoretical Physics. So if you continue into the option of applied maths and fluid dynamics, you could actually get the chance to see some experiments. I don't think you'd actually be doing them yourself, but you probably actually get the chance to see some of these experiments in fluid dynamics in damped.
Great, thank you. We've had another, I think this looks like a really great question. Here we go. Are the interview questions all about getting the answers or more about the process of solving?
Yeah, definitely more about the process of solving. Okay, so we might ask you a question, and if you said straight away, numbers divisible by 9, full stop, then we'd be like, well, how did you get to that? Okay, so we very much want to see how you think about maths, see how you solve things. Very often we don't even get to the end of the question that we're asking you, and that's absolutely fine. We're more asking you about, we really want to see how you think along the way.
Fantastic. Okay, I think we've run a couple of minutes over, so we'll stop there. There are lots of questions in the chat and lots of really great questions. So I will just say to everyone, please do feel free to drop outreach. It's outreach@murrayedwards.cam.ac.uk. You can drop us an email and we will do our best to answer your questions, or I can try and find the answers for you. But I think we do have to stop there, particularly if you have any questions around. I know there's been a couple of questions about the STEP residential. Please do feel free to drop us an email about that. If your question is more admissions related, to do with applying for maths, you can also email admissions@murrayedwards.cam.ac.uk. But I just want to thank you, Zoe. That was really brilliant. Thank you so much. And it's been really great having you all attend.
Thank you very much.
Great, thank you.